Hi to everyone. I'm Dr. J. Krishna, Associate Professor, Department of AIML, Namacharya University, Rajanpet. I'm going to demonstrate in this presentation advanced data structures and algorithms analysis, Heaps concept. So this presentation shows you what a heap is and demonstrates two of the important heap algorithms. A heap is a certain kind of complete binary tree. So this tree to be appear like this. So tree consists a root. So when a complete binary tree is built, its first node must be the root. Then left child of the root, considered as the second node, is always the left child of the root. Then right child, the third node is always the right child of the root. The next nodes always fill the next level of left to right. So similar way, all the remaining nodes are constructed. So then it is called as complete binary tree. So this is a example, a heap. So kind of complete binary tree. So in this tree, each node in a heap contains a key that can be compared to the other nodes keys. So the comparison like this. So 42 node is a right of 27, and this property to be verified here. Adding the node to the heap means so that 42 to be appear at the right child of 27. So put a new node in the next available spot. So that is 42 location and it's a right child of 27 node. So then push that new node upwards. So verifying that property of heap, swap with its parent until the new node reaches an acceptable location. So in this case, 27 is a lower value and 42 is a higher value. So the swap to be appear, and after swap, this variety of tree to be appear. Then the same it is to be verified for the remaining nodes in upwards. So like 32, 35 and 42. So 42 is the higher value. So it upwards to 35 node. And similarly, 45 and 42, here comparison to be performed, and there is not required swapping because of 45 is a higher value and 42 is a lower value. So the property of heap, it is like the parent has a key, so that is greater than or equal to new node, or the node reaches the root. So this is the property. Here it is to be verified after adding a new node. So the process of pushing a new node upward is called as reheapification upward, and removing the deletion the top of the heap. So move the last node onto the root. So this process to be performed in removing or deleting the top node of the heap. Remove uh, last node to the root. That means a root to be deleted, and then after verify the heap property to the remaining uh, child to the root. In this connection, 27 and 42 compare and whatever higher value is there, so that swap is required, that swap you have to perform. That is called as uh, downward push. That swap with its largest chain until the new node reaches an acceptable location. So this is the 42 and 27. 42 is the higher value swap to be occurred, and 27 comes as a left child of 40. Similarly, 35 and 27, the swap is required. Here, 27 appears as a left child of 35. So similarly, verifies that 27 and 19, 19 and 27. 27 is a higher value, so it is a parent, and 19 is a lower value to the 27. So there is no appearance of any factor. So this is the final reaching property, and after removing root node, the child all have keys like less than or equal to the out of place node, or the node reaches the leaf node. The process of pushing the new node downward, so is called as a reheapification downward. So implementing a heap, this is to be like this, and is a is a simple heap with uh, 5 nodes, and 42 is a root node, and 35 is a left child, and 23 is a right child, and 27 is a 35 is left, and 21 is the right 35 right child. So it is a heap tree, and we will store the data from the nodes in a partial filled array. The array appears with subsequent memory locations. That memory locations you have to understand by seeing these particular partitions. So then root comes into the first location, or first partition of the array. So then after left child and right child, it comes in the next subsequent memories, like this 35 and 23. So similarly, the remaining childs also uh, occupied their array locations like this 27 and 21, left child and right child. So this is called as a implementing a heap in the form of array. So next to two locations as empty, and that locations no worry about, and no care about that remaining uh, empty parts, empty locations of array. So the important points about the implementation, the links between the three nodes are not actually stored as pointers or in any other way. So the only way we know that the array is a tree, so is formed the way we manipulate the data. So that data appears like this type of array uh, memory locations. So if you know this index of a node, so then it is easy to figure out the indexes of that node's parent and children. Formulas are given below. So that formulas to be like this. So the root element will be a array of 0, and the table shows the indices of other nodes for ith node, that is a of I. So a of I minus 1 by 2, so returns a parent node, and a square bracket of 2I plus 1 returns a left child, and array of 2I plus 2 returns the right child. So these formulas are applied in array implementations of heaps. The heap quick understanding of heap. Here you have to understand a heap is a complete binary tree. So where the entry at each node is greater than or equal to the entries in its children. To add an entry to a heap, place the new entry at the next available spot and perform a reheapification upward. So to remove the biggest entry, so move the last node onto the root and perform a reheapification downward. So these are all as quick references. So with the support of this heap concept, there is a way to efficient data handling as the outcome you may expect from this concept. So thank you. Thank you, one and all.